Hello, and welcome to Agrosive Physics. Today is day 127, and what I'd like to do today is discuss the right-hand rules for magnetism. And this will allow us to determine the direction of the magnetic field. Now there are three right-hand rules, and the first thing you need to do is make sure that you know which hand is your right hand. So I'm going to use my right hand for this, and what we're going to be able to do is use the three aspects of your hand in order to determine the direction of the magnetic field. If you hold your hand flat like this, you can realize that it really acts as a plane, an XY coordinate system, and your palm points in the Z direction. So this is an XYZ coordinate system. I've seen some textbooks use your index finger pointing forward, but I like to use the palm of my hand to represent that direction. Your fingers point in one direction, your thumb points in another, they're perpendicular, and your palm points outward. If you remember coordinate systems that are X and Y, the X and the Y axis are perpendicular. If you have a three-dimensional system, which is why we need to use the right-hand rules, because magnetic fields exist in three dimensions, you need the Z. So your fingers here, as you have it here, your fingers and your thumb are perpendicular, but then your palm acts as a third dimension and points outward. So you're going to be able to use your right hand to determine the direction of a magnetic field in a problem. Now the first right hand rule is if you have a wire and you have current flowing through the wire. Remember, moving electrons create magnetic fields. Now the right hand rule is one that I use because I'm left-handed. So when I'm writing with my left hand, my right hand's free. All of these right-hand rules can be used as a left-hand rule if you follow the direction of electron flow. But since I learned conventional current when I learned about physics, I'm going to use right-hand rules. And this means this is the direction that protons move. So if I have a wire like this, and of course this is a pencil, but if this pencil can simulate a wire, and I have the positive flow, the protons are flowing up, the right-hand rule says the following. You place your thumb in the direction of conventional current, which is the direction the protons move. So that means I would have a negative terminal here and a positive terminal at the right. That would be, if I have negative and positive, the protons would move down. So I'm going to put my thumb down the wire. Now my fingers are wrapping around the pencil in the direction of the magnetic field. So the magnetic field is going to act like this. Now if I were to use electron flow, I could actually use my left hand to do this. The electrons would flow up. I could use my thumb of my left hand and wrap my hand around the wire. My fingers wrap around like this, and the magnetic field is in the correct direction. So either way you have your hand, if it's thumb up to represent the electrons or thumb down to represent the protons, your fingers are wrapping around the wire in the same direction. So right-hand rule 1, and remember, I'm going to use right-hand rule, so I'm always going to use the direction of proton flow, is going to be put your thumb in the direction of the proton flow, and then your fingers wrap around the wire in the direction of the magnetic field. So in this case, the magnetic field flows in this direction. That's right-hand rule 1. Now right-hand rule 2 deals with a solenoid. Now what's a solenoid? A solenoid is a fancy name for an electromagnet. And if you have an electromagnet, that means you can choose when it's magnetic and when it's not. It's important if you're trying to lift cars, let's say, to have something that you could turn off the magnetic field. If I were to lift a car with a crane and it was a permanent magnet, I wouldn't be able to remove it. So with an electromagnet, what you have is wire that's wrapped around something, and that creates the solenoid. So right here, I have a miniature solenoid. Now, of course, if you have a solenoid, inside what I'm wrapping it around will help the magnetic field. A pencil's not going to do its job. So if I were to wrap this around a piece of metal, maybe a piece of iron or a piece of steel, it would increase the strength of the magnetic field. The solenoid in this case, you need to take your fingers and you place them in the direction of the proton flow. So in this case, if I have the protons flowing around my pencil like this, I'm going to wrap my hand around the pencil, and right hand rule 2 says your thumb points in the direction of the North Pole. Now the same could be said for the left hand. If you were to do the left hand rule, you would follow the direction of electrons. Now if protons flow around this way, into and around the solenoid like this, electrons would flow the other way. So I would take my left hand, I would wrap it around underhand basically, and my thumb would still point in the same side. So the North Pole of this would be here, and that would mean the South Pole is on the other side. So a solenoid is effectively wrapped wire around something, and you can create a magnetic field from that. Now that's right hand rule 2. Many students have made a solenoid, possibly in elementary school, when you learn about magnetism. A lot of people wrap wire around a, usually it's either a screw or a nail, typically a nail, and you connect it to a battery. The battery could be a 9-volt battery, for example. Now when you do that, you are creating a solenoid. The North Pole is on one side and the South Pole is on the other. We can determine that by using the right hand rule. Remember, your fingers point in the direction of the proton flow, and your thumb is the direction of the North Pole. And that's right hand rule 2. Now, right hand rule 3, you need to take your hand and hold it flat. And what you're going to do is be able to determine the magnetic field, the direction of the magnetic force on a wire. If I were to take a wire and place it in a magnetic field, it wouldn't do anything. If I were to turn the electricity on in that wire, it would then interact with the magnetic field. In fact, it could be repulsive or attractive depending upon what I did. Now, the way this works is you need to know the direction the magnetic field is acting. Now, in between a horseshoe magnet, you have a uniform field, very similar to the parallel plate with the electric field. So what you can do is take your hand and you place your palm in the direction of the South Pole. So your palm can point in the direction of the South Pole. Your fingers point in the direction of the proton flow, the conventional current in the wire, and then your thumb is the direction of the force. So if I have my horseshoe magnet here, and the South Pole points that way, if I were to take my protons and face them towards you, toward the camera, what would happen is the force on the wire will be up. If I were to switch this around and have it come toward me, what will happen is, as I face the South Pole that way still, the force will be down. So depending upon the direction of the field, the protons, and finally you could find the direction of the force on the wire. And the wire would actually move within the field. It would just sit there normally, but as soon as I turn on the electricity, it would either move down or up depending upon that situation. Now, even though we dealt with right hand rule 3 for protons flowing through a wire, now remember, the electrons are what's really moving. Conventional current is what scientists used to believe was happening, and it still works if you use your right hand. Electron flow, stick to your left hand. Your palm is still the direction of the magnetic field. Your fingers are the direction of the electron flow, and then your thumb is the direction of the force. The fact that I was pointing my fingers toward the camera means we have three-dimensional space. And what we're going to have is difficulty defining that on two-dimensional paper or two-dimensional board. So what we have are rules for denoting in or out of the page. And the way we do that is we think of an arrow. If I were to fire an arrow at the camera, what would happen is I would see, the camera that is, you would see a dot, the point of the arrow coming at you. I would see, on the other hand, the feathers on the back of the arrow. Now the dot represents the arrowhead, and the feathers we represent with an X. So if you have an X on a piece of paper, that represents into the page. Dots on a piece of paper represent out of the page. So we can denote the X and Y coordinate axis on the page itself because it's already two-dimensional, and then in or out of the page will be denoted by X's or denoted by dots. Dots are out of the page and X's are into the page. And you can remember that by thinking about what you would see if you had an arrow coming at you, you'd see the point, and if you saw the feathers or the flight of the arrow, you would see an X. I understand that because of fletching, you wouldn't have the full X, so you could actually shoot the arrow. But I'm thinking about a standard just arrow like you would just have as a toy, let's say. So you'd have the X representing into the page and a bunch of dots representing out of the page. So that being said, you can use right hand rule 3 to represent a single charge, and your hand would do the same thing. You hold it flat, your fingers point in the direction of the proton's motion, your palm represents the direction of the field, and your thumb represents the direction of the force on that charge. Now, if you had an electron, you can either use your left hand to do that or use the right hand rule and then flip your answer at the end. So you have a number of choices, and it's up to you to determine which one is more comfortable for you. If you're already right-handed, you have your left hand free when you're working, so you may want to do the left hand rules. For me, I'm left-handed, so the right hand rules were natural, so I didn't have to put down my pen and lose focus. So right hand rules represent proton motion, left hand rules would represent electron motion. What we'll do at this point is take out the whiteboard, and I think it'll be easier to show you a number of sample problems dealing with the right hand rules, and then you'll be able to see how they are useful. Right hand rule 1 was for a field around a wire. Thumb points in the direction of the proton flow, and your fingers wrap around the wire in the direction of the magnetic field. So magnetic fields are circular around wires. With a solenoid, you had a wire wrapped around something, your fingers wrapped around in the direction of proton flow, and your thumb was the direction of the North Pole. Finally, right hand rule 3 was either for a wire or a single point source. Your fingers were the direction of the charged particle. If it's right hand, it's proton. If it's left hand, it's electron. Your thumb is the direction of the force, and your palm represents the direction of the magnetic field pointing to the south. That's it for right hand rules. I think we'll take the whiteboard out, and I'll show you some sample problems now. Thank you. All right, the right hand rules are useful for finding the direction of the magnetic field. And magnetic fields exist in 3 dimensions. So we have the XY coordinate system, and we also have the Z coordinate system as well. So we have a situation where we have 3 dimensions, and we have to represent it in 2-dimensional space. So it's easy if we have the magnetic field going in an X or a Y direction, like this or this. And remember, B is our symbol for the magnetic field. But we also could have the field coming out or going into the page, because as I said, that's the Z direction, out or in. So what we do is we denote that with a dot representing out, or an X which represents into the page. Now the way I remember it is I think of an arrow. We have an arrow with the feathers on the end, the fletching, and if the arrow is coming towards you, which would represent the out, you see the tip of the arrow. If it's going away from you, you'd see the X. Now I understand a real arrow doesn't have a full X so that it can actually move across the bow, but we'll look at an X, and that's just how I remember it. It's into the page, because as you shoot the arrow away from you, you'd see the feathers or the fletching. So we have arrows that represent the direction of the field. Left, up in this case, out, or in. And if we had out, we typically just do a bunch of dots like this. A uniform field that represents out, and maybe we'll have a uniform field here that represents in. Now the field can be represented left, right, up, down, in or out, but also the direction of charges that move within the field, or a wire, the current in the wire within the field. So this could be a wire going out of the page, a wire where the protons are moving into the page. And the right-hand rules represent positive charges. There is an alternative where you'd use left-hand rules, where you'd use your left hand to do these, and that would represent negative charges. Now what I typically do is I'll use right-hand rules, mainly because I'm left-handed, and I know that I don't have to pick up my pen and constantly put it down during a test. But That means if we're dealing with an electron moving through a field, at the end of the problem, what we're going to have to do is switch it. So if the force, for example, or for an electron, it goes to the left, the reality would be that it goes to the right. Now, the other thing you need to do with the right-hand rules is realize that you have three parts of your hand. If you hold your hand flat like this, you have three dimensions. You have the plane of your hand itself, you have the palm of your hand coming out, and then you have your thumb. So the three directions are represented in a flat hand like this. X, Y, and then out would be Z. So you have your three dimensions with your right hand. So we're going to use those right hand rules to analyze the different directions of the magnetic field or the forces on charged objects within the magnetic field. So let's talk about the actual rules themselves now. All right, the first right-hand rule, rule number 1, is representing the field around a wire. And if we have a wire where the charge is flowing up on the page, and that's the direction of positive charge, and I know that positive charges don't move, but the right-hand rules represent proton motion. What you're going to do is you're going to place your thumb in the direction of the wire, in the direction of the current flowing through the wire, and your fingers will wrap around in the direction of the field. So what I'm going to do is I'm going to take my hand and I'm going to place it so it points up, my thumb is up, and my hand will wrap around the field. So on this side, my fingers go into the page, so I would represent that with X's. And then on the other side, my fingers come out of the page, and I would represent it by dots. The field itself is circular, and it goes in and out. So each one of these represents a circular pattern that goes up and around into the page and then back around. And since I can't represent the three dimensions that way, what I do is I use the X's and the dots. What I'll often do is I'll use my pen or pencil to represent that as well. I'll physically wrap my hand around the pen, in this case my marker, and that will show the direction of the field. If I were to have a wire coming out of the page, like that, there's my wire, I could represent it with my marker. I'd wrap my thumb and I'd wrap my hand around the field like this. So the magnetic field would look like this, circular. And I draw the arrow in the direction my fingers point, and that shows the direction of the South Pole. So the South Pole is going in this direction. That's the direction of the field. If it were into the page, I have my wire now pointing in, the protons are moving down into the page, it would wrap around the opposite direction. It would look like this. Now what could happen is you could have two wires having the field, and then in this spot they're going to interact. And when they interact, you can either have repulsion or attraction. And what's interesting is we have the fields doing the same thing in this case. So what that's going to represent is actually repulsion on the wire. If you have the same direction, they actually pull in. And that'll be more evident when we do one of the right-hand rules. I think it's rule 3 will be useful for that. We'll be able to see the attraction and repulsion on two wires. But right-hand rule 1 is you put your finger in the direction of the current flow, and you wrap your fingers around the wire in the direction of the magnetic field. All right, right-hand rule number 2 represents the field around a solenoid. And a solenoid, as I said before, is a fancy name for an electromagnet. What we typically have is wire wrapped around some kind of core, usually made of iron. And we'll take the wire and we'll wrap it around. And this will represent a three-dimensional space. And what will happen is I can have the protons flow around the core in this direction. So what I do is I take my fingers and I wrap them around the core. So I'm holding the core itself, wrapping my fingers in the direction of the proton flow, and my thumb now represents the direction of the North Pole. So this would be a North Pole of the bar magnet, and this would be the South Pole. Now I could have the same situation, but I can wrap it underneath first. Oop, yeah, there we go. And now if I have the protons flowing this way, under and over, under and over, under and over, it's hard to represent the 3 dimensions even with the drawing here, but I'm going to wrap my hand underneath. My fingers go in the direction of the protons, and my thumb is representing the direction of the North Pole. So in this case, I'd have a north and I have a south. And assessment questions will ask things like, what will happen to the 2 solenoids? Will they be attractive or repulsive? So the first step would be determine where the north and south poles are, like I just did. And then what I would do is realize that we have 2 souths next to each other. So the interaction would be that they would repel one another. You could even have a compass nearby, and it would say what pole points towards the solenoid. For example, if I had a compass over here, it would ask how would the compass act, and it would line up here. This would be the south pole of the compass, and this would be the north pole. And really there's 2 ways you can wrap wire around a solenoid. You can either wrap it around forward, if you will, or underhand. And if you wrap it forward or above, your thumb is going to be to the left. And if you wrap it under, your thumb is going to be to the right. So that will change where the north and south poles are. So in this case, we'd have 2 south poles interacting. They'd repel each other, so the force would be repulsive. So right hand rule 2 is really taking a single wire and just wrapping it around some kind of core, mostly iron. So that's right hand rule 2. Okay, right hand rule 3 has 2 parts. I call them A and B because they use the same hand structure. And what you're going to do is hold your hand flat. And when your hand's held flat, you have 3 parts to it. You have your fingers, you have your palm, and you have your thumb. And your fingers are going to be the direction of the current, so current flow. Your palm is the direction of the magnetic field, the south pole, the direction of the south, and then your thumb is going to be the force. And there'll be a force on the wire itself as the current is flowing. So what we can have is a situation where maybe the magnetic field is into the page. And what I'll do is I'll take a wire and I'll make the current flow to the right. Now the way I do this is I'm going to take my hand and I'm going to put my palm into the direction of the magnetic field. Now, so that means my palm is slapping the table itself or the paper. My fingers are going to go in the direction of the flow, and my thumb is going to represent the force. So in that case, with right hand rule 3A, the force on the wire would be toward the top of the page. So that means the wire, if the field's strong enough or the current strong enough, would actually move upward. Now I could have another situation perhaps where the magnetic field perhaps is to the top of the page, and I will put let's see, the wire vertically. Let's put the wire vertically. And I'm going to use an X to represent the wire. So the wire's vertical like this. The current is flowing down into the page, and my magnetic field is up. Now, the problem with the right-hand rules sometimes are that your hand is awkward. It's hard to place your hand in these directions. So I don't have the opportunity of moving my paper around. So what I have to do is I have to stand up. I'm going to place my fingers down into the page. My palm is slapping the top of the page so that south is up that way, and my thumb is pointing to the right. So in this case, the force would be to the right. Now, it's important to realize that you need to have perpendicular motion between the field and the current. If you had the field going up, there's your B, and the wire, let's just have it going down, the current flows down, I can't have my fingers and my palm pointing in that same direction at the same time. So there would be no force in this case. You have to have perpendicular motion between the two. So the field and the flow have to be perpendicular. So field has to be with an L, has to be perpendicular to the current flow. Field perpendicular to the flow. If it's parallel, no force. And that's right-hand rule 3A for a wire placed in a magnetic field. Right-hand rule 3B is very similar to 3A in the fact that you use your hand flat. So you're going to have your hand flat like this. Your fingers are going to represent the direction of the charged particle, in this case a proton. So fingers is the proton motion. Your palm is the field, so B, and your thumb is the force. So we're going to take a proton and we're going to shoot it to the right. It's going to have a field that's out of the page like this, and we're going to figure out what direction the force is. That means my palm is up and my fingers need to point to the right. Now, I had to get up to do that, but it shows that the force when it enters the field is going to be down. What that's going to do is cause the proton to move in a parabolic path. Now, if we have enough of a field, it can actually cause the proton to go in a circle. Now, what's important to note is that this force is going to be perpendicular to the motion. So it's actually a centripetal force. And if it's a centripetal force, it does no work. Because if you remember, we need to have work as force times distance, but that force had to be in the direction of motion. And since it's perpendicular, there's actually no force in the direction of the motion, so you get no work caused by this magnetic field. Now, let's say we had another situation where we took an electron. What you could do is you could switch to your left hand. That would show the force up. Or you do the same thing with your right hand. And then although my thumb points down, I flip my answer at the end, and the force would be to the top of the page. So in that case, an electron would spin that way. Still the force is centripetal, still does no work, the field's doing no work, but we can ultimately figure out the radius of this once we have some equations. But right-hand rule 3B deals with the charge in a field, and use your fingers to represent the direction of the charge, your palm represents the direction of the field, and your thumb represents the direction of the force. They have to be perpendicular or else there's no force at all, and the force is perpendicular to the motion, which is a centripetal force, meaning it does no work.